we will find the electric field intensity on a point P in space due to a line charge distribution. So to calculate that, we will assume that we are having a line charge distribution. We'll take the symmetry for this case, and if you're saying this is my x coordinate, this is my y coordinate, and this is my z coordinate, then I'll assume that this my charge is located along the z axis. So drawing that, so this is how my charge distribution will look like. So my charge is the line charge which is located along the line charge which is located along the z axis, so this is my charge, and the charge is can be shown in an area of PQ on the z axis. And to consider this, I am taking that there is an infinitely small element of charge which is known by dl. So by line charge density, I can say that my charge dq is equal to the line charge density into the distance. So this is my infinitely small charge. So rho L is equal to the charge per unit centimeter or charge per unit meter. So this is known as line charge density, which I have to consider. So this is what it looks like. So this is my charge dq, which is equal to rho L into dl. So my equation for force is equal to k q1 q2 divided by r square into r vector, and my equation for electric field intensity is equal to force divided by q. So I will be having only one charge here, so I am considering the q2 to be my test charge, which is located somewhere here. So again, that will give to my equation as k, and the charge will be ql, which will be equal to the line charge density. So it will be the integration of the charge, full charge across my line. So this is a line integration of q dq or dq and the vector r and the r square. So this is how this equation will be used to find my charge distribution or the line charge distribution. So the first step was to find my dq, and I have taken an infinitely small length of dl, which is located at 0 0 z1, and my q point is located at 0 0 z2 if I am simply considering that. So this is my vector r, which is located from the point dl or dl to, which is located at 0 0 z1, and from to the point r where I want to find the field intensity. So the vector is known as the r vector. So the r vector, so if I am taking a summation of the r vector, is a summation of two vector. One is from the origin to, if I am taking this, if I am considering, if I am just for reference, if I am giving this point m, so the r vector is a summation of om vector plus mr vector. So the om vector, it can be written as az1, simply z1 az, plus the mr vector, which is the point here has x, y and z. So it will be xax plus yaz plus zaz. So this is how you will find the r vector, which is used here to find the distance. So you'll have to take, so this, if you are having the values, so if this is a problem which is given, if you have the values of ax, ay, az, or if you have the values of x, y, z, it's directly possible to calculate it from here. But if you don't have the values, it's possible to consider if it is possible to take this into spherical coordinates, and when you are taking this into spherical coordinates, what you can see is that you can take a cylinder of radius rho, and when you are taking that, you can see that your, if you are considering this to be my z vector and this to be my rho vector, so again you can see that the r vector, this is in Cartesian coordinates, so this is possible to write this in Cartesian coordinates. But to again simplify, if you are taking the spherical coordinates, it can be simplified further as the r vector plus the z vector, which is a vector, if I am considering this m and this is q, so the mq vector is equal to qr vector, that is this vector. So the qr vector is equal to rho a rho, and the mq vector is equal to z2 minus z1 az. So simply I can take this as z or z3 az to simplify it. So this will become something like the r vector is equal to rho a rho minus z3 az. So if I am considering this my first equation and this as my second equation, so I have found the value of r, which is this is a r vector. I have written it in small letters, but considering our figure, we can write it in same way. No, so now it's possible to write the equation as f is equal to k, and from here what you have is dq. So your dq will be rho l, and dl, your what is your dl will be dz1, or it will be simply dz because it is in z direction. And then this is integration of from minus infinity to infinity, because you are considering the z here, and your r you will have to substitute here as rho a rho minus z3 az divided by rho square plus z3 whole square raised to 3 by 2. This is a vector, this is a unit vector, so this was a unit vector, so it will be like if this was my r vector, unit vector divided by r square. So this unit vector can be written as r by r. So when I am multiplying it into this, can be it will become 1 upon r square. So it will become 3 by 2, 3 by root 2, because this will be 1 upon root 2. So that's how you have got this. And now you will have to solve this integration, and when you are solving this integration, you will have to keep in mind that you will get something like this. You will get f is equal to k, and you will get infinity to infinity minus infinity to infinity. You will get rho l and into rho, which is this rho which you are getting here, and into dz divided by rho square plus z3 square raised to 3 by 2. So again, what you will need to keep in mind is that while calculating the force, you can simply cancel this AZ part, since there will be no force. So if you are considering a force due to the line charge, it will be only in this direction. There will be no force which will be happening in the top direction or the AZ direction. So the force due to the Z component will be 0. So you will get something like this. After you are putting this to 0, this part is equal to 0. uh, and now to solve this full thing, you will have to do a substitution. The substitution which you will have to take is, you will have to substitute the rho is equal to, or Z3 is equal to rho cot theta. So this is my theta and this is my rho. So when you are doing the substitution and you are solving it based on the trigonometry tables, so what you should get is, you should get, this is for electric field intensity. So what you should get for electric field intensity in the direction of the rho is, should get it as rho L divided by 2 pi epsilon naught rho. So this is the electric field intensity due to a line charge along the z axis. But you can say that if the line charge is along any axis, this equation will be valid, and this is at a point P, or at any point P which you are finding the electric field intensity, the equation will be like this, and this is how you are deriving it.